Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresh University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Hello, good afternoon, everyone, and good afternoon, all the audience here, right? And also good morning for the speaker. Okay, so welcome to IF Colloquium number 21. And today we have a guest speaker from Queen Mary University, Timothy Clifton. He's going to talk about testing gravity in cosmology from the solar system to the entire observable universe.
Okay, thank you very much, Tirupab. Can you hear me okay?
Can you just share your screen? You can start now.
Okay, let me just share here. Can you see my screen? You can see my screen here?
Yes, we see now. Thanks.
Okay. So it's a pleasure to be speaking to you today. Greetings from London. And as Tirupab says, my talk today is going to be about testing gravity in cosmology, from the solar system to the entire observable universe. So here I wanted to start off by describing how tests of gravity work within our own solar system, which is where they're most well established and most accurate at the moment, and how I've been thinking about trying to extend these tests so that they can be applied in cosmology on the scales of the entire observable universe. So as we're talking about testing gravity, it seems appropriate to have a historical timeline of the big developments that have happened in gravitational physics. And let me start at the very beginning here with the 4th century BC in the ancient world with Aristotle. So Aristotle had an enormous influence over modern science, of course, and his books on physics, which gave the subject its name, and on the heavens, he came up with an explanation, a qualitative explanation for how he thought bodies moved under gravity. So Aristotle's approach to this problem wasn't scientific in the modern sense, but it was more looking for a qualitative understanding. And he based his understanding on what were thought to be the 4 elements at the time. So it was earth, water, air, and fire. And Aristotle's idea was that objects would try to move to their natural place in the universe according to the elements that they were constructed from. So Aristotle's physics was, as I say, extremely influential and lasted for around 2,000 years as the dominant explanation of theory of gravity, at least in Europe, before it was supplanted in the 17th century by Isaac Newton's great work in the Principia Mathematica. So Newton revolutionized not just what we thought about gravity, but how we did theoretical physics at all. So Newton made gravitational physics a quantitative science and made predictions not just of the motion of objects on and near the Earth, but of the Earth itself and of the other planets in the solar system. Newton's theory of gravity for a long time was thought to be the final word on gravity, such was its success, until, of course, in the early 20th century, when Albert Einstein developed his theory of relativity. So Einstein's theory of relativity replaced Newton's idea of an external force that acts between bodies with the idea that gravity is in fact a manifestation of the curvature of space and time itself. So it's an extremely elegant...
Sorry, can you just move your microphone a little closer, because sometimes the sound just kind of going down a bit.
Okay. I'll try and speak a little louder.
Yes, I think that's better.
Okay then. So Einstein's theory of gravity, of course, is our current best theory, our best description of how gravity works. And from the modern perspective, we think of Newton's gravity as an approximation to Einstein's theory in some appropriate limit. And correspondingly, one can think of Aristotle's physics as an approximation to Newton's gravity as well in some appropriate limit. So I'm not going to talk anymore about Aristotle's ancient work on physics. There's a very nice paper on the archive you can find by Carlo Rovelli that discusses this and how Aristotle's ideas fit into our modern understanding of gravity. But I'm going to start with a description of a critical description of Newton's gravity. So Newtonian gravity, of course, is well known to all physicists. But let me give you a description that will be useful, I hope, for the type of tests of gravity that I'm going to be talking about today. So Newton's gravity has a number of ingredients that go into it. So these are the level of assumptions on which the theory is built. The principal among these are Newton's ideas about what space and time are. So Newton understood space and time to be absolute concepts, such that we define motion with respect to absolute space and dynamics with respect to an absolute time that's shared by all observers in the universe. Another ingredient that went into Newton's theory was the equivalence of gravitational and inertial masses. So these are the masses that are responsible for the generation of a gravitational field and the response of a mass to an external force. Newton supposed these to be the same. And as well as this, his universal law of gravitation, which is, of course, is proportional to each of the masses involved in an interaction and inversely proportional to the square of the distance between them. So with these ingredients, Newton was able to calculate a large number of physical outcomes that his theory predicted. And in fact, so successful was this theory that it's still used today by most physicists who are doing astrophysics as the dominant contribution to most types of gravitational interactions. Much of the language on gravity still uses the concepts that Newton developed in his theory. So if we're going to apply the scientific method to Newton's theory, then we need to ask if these ingredients that go into the theory are valid and if the outcomes that are predicted by his theory are testable. So let me go through my brief list here, which isn't supposed to be exhaustive, but is some of the relevant topics, I think, for this talk. Let's start with absolute space and time. Well, we now know that there is no such thing as absolute space and time. Of course, Einstein's theory revolutionized our understanding of these concepts. But even before Einstein developed his theory, there were good, sound philosophical arguments by Ernst Mach and others that told us that theories shouldn't involve unobservable quantities such as absolute space and absolute time. We know Mach's principle was one of the big motivations for Einstein to develop his theories. The second ingredient on the list here, the equivalence of gravitational inertial mass, well, as far as we can tell, that is in fact valid in the universe. And the third ingredient here Newton's universal law of gravitation, we now know is not correct. And of course, that was the primary motivation for Einstein to develop his replacement, the fact that Newton's law of gravity would appear to propagate instantaneously from one body to another that's separated at different points in space. And Einstein knew that this couldn't be true because his special theory of relativity meant that signals couldn't propagate faster than a fixed speed limit, the speed of light. And amazingly, it seems that Newton was aware of this flaw in his theory as well. So I've got a quote here from a letter that Newton wrote to one of his contemporaries, Huxley. And I quote here from Newton, that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that, I believe, no man who is in philosophic matters a competent faculty of thinking could ever fall into it. End quote. So it seems that Newton was well aware of this action at a distance problem that was the primary motivation for Einstein. So some of the ingredients of Newton's theories, we now know with the benefit of hindsight, aren't valid. What are the outcomes, the predictions that Newton made? Well, as I was mentioning before, very many of the predictions are accurate enough that they can give us the leading order behavior of the majority of gravitational physics in the solar system and other astrophysical systems. But we now know that there are observations that cannot be explained by Newtonian gravity. So Newton's theory doesn't explain the motion of all bodies under gravity, as it was once thought that it might do. In particular, the first observation that was found to be incompatible with Newton's theory was the orbit of the planet Mercury. So this was found at the end of the 19th century. It was found that the perihelion of the elliptical orbit of Mercury around the sun precessed at a rate that couldn't be explained by the Newtonian gravitational fields of the other bodies in the solar system. And this was a significant enough problem that it was hypothesized by astronomers at the time that there might be another planet between Mercury's orbit and the sun. And it might be that planet's gravitational field that was influencing Mercury. So this has echoes of what's now done in the field of dark matter research, I think, where new unseen gravitating bodies are introduced into a problem to try and explain observed gravitational phenomena. Of course, there is no planet between Mercury's orbit and the sun. So that hypothesized planet, which was called Vulcan, is no longer needed. And we now know that it's Newton's theory itself that needs replacing by Einstein's theory of general relativity. Another outcome of Newton's theory that's not satisfactory is its explanation of cosmology. So I've written this on the slide here as Seeliger's paradox. So it's not that Newton's theory can't be used to describe an infinite number of masses. The problem is that the gravitational influence, the motion of bodies under the gravitational influence of infinitely many other bodies is not unique. So it turns out that the expansion of infinitely many bodies away from each other depends on the order in which you sum up their gravitational potentials in Newton's theory. So doing it in different ways leads to different answers. And that apparent paradox is Seeliger's paradox. And again, we know that the solution to this paradox is to abandon Newton's theory and to use its replacement. So that brings us on to Einstein's general theory of relativity. So just as with Newton's theory, Einstein's general theory of relativity has got a number of ingredients that go into it. So principal among these, I'd say, would be local Lorentz invariance. So this is the idea that in a freely falling frame, we ought to recover the laws of special relativity up to the influence of tidal forces. A second ingredient is the equivalence principle. So this is a generalization, an elevation of Newton's idea of the equivalence of gravitational and inertial masses to a new type of principle, which Einstein used as one of the ingredients for his theory. And the third ingredient that I've got listed here is Einstein's field equations themselves. So these were a replacement for the Newton's universal law of gravity. And instead of formulating an external force that acts between bodies instantaneously, Einstein's field equations tell us the relationship between the curvature of space-time and the energy and momentum of the matter fields that fill that space-time. So again, this isn't an exhaustive list, but these are some of the primary And as for the outcomes, well, Einstein's theory is highly predictive, and it predicts a number of different gravitational phenomena in the solar system. A leading order, it reproduces Newton's theory, but as well as this, it predicts a plethora of other small relativistic effects that can be searched for and have been searched for and found in the solar system. I'll talk through some of those in a moment. Another outcome is the prediction of gravitational radiation. So this is propagating waves in space and time itself. This was a prediction that was made by Einstein himself very early on. And now with Einstein's general theory of relativity, we have a way to self-consistently describe cosmology. That is the behavior of the entire universe under his theory. So our goal as modern physicists is to try and probe our understanding of Einstein's general theory of relativity. So we can ask the same questions and apply the scientific method to Einstein's general theory of relativity. Are the ingredients that go into that theory valid? And are the outcomes that it predicts testable? So let's go through these ingredients and outcomes as we did with Newton's theory. So local Lorentz invariance, as far as we've been able to tell so far, is a symmetry of nature. And this was shown early on by, in the 19th century by Michelson and Morley in their famous experiments. The modern version of those types of experiments are the huge Rever experiments, which look for anisotropy in space, and they show that there is no such thing, an accuracy of around 1 part in 10 to the 27. So this is a phenomenal level of accuracy, which leads us to believe that local Lorentz invariance is indeed manifest in nature. The second ingredient on the list here, the equivalence principle, well, that would require that all masses in vacuum fall at the same rate under gravitational fields. And as far as we can tell, the weak and Einstein versions of the equivalence principle are also valid. There's been no experimental evidence to show anything otherwise. And the first high accuracy experiments of the equivalence principle were performed by Yertverse with a torsion bar. They had accuracies of around 1 part in 10 to the 10. The modern version of those experiments, the most modern version I'm aware of, is the microscope experiment. So this is a space-based test of the equivalence principle, and it measured that masses with different compositions fall in vacuum at the same rate to within 1 part in 10 to the 15, which is the experimental error on those experiments. So the Lorentz invariance and the equivalence principle have very strong evidence indeed in favor of their validity. The third ingredient that I've got on this list, Einstein's field equations themselves, well, whether or not they're valid is a topic of open research at the moment. And I'd say that there's good reasons to suspect that they may not be valid as fundamental laws of nature, particularly from studies of quantum field theory. So if one were to try and perform a perturbative quantum field theory of Einstein's field equations, it's very well known, of course, that one's led to contradiction. Unsatisfactory results. So I'll put a question mark there, as that's an open question, I think. And let's move on to the outcomes, the predictions of Einstein's theory. So gravitational physics in the solar system. Over the last 100 years or so, there's been a very large number of experiments looking for the small predictions that Einstein's theory makes over Newton's theory. And to date, all of those observations have been consistent with Einstein's equations, which is really a phenomenal achievement to make, given he wasn't aware of most of these experiments could take place when he constructed the theory in the first place. So there's very many different phenomena here, which I'll talk about in a little bit more detail as the talk goes on. The second outcome, gravitational radiation. Of course, recently and very famously, this has been verified as well. The first indirect evidence of gravitational radiation came from the Hos-Taylor binary pulsar. So in that system, we see two neutron stars orbiting each other, and their orbital radius decreases as they emit gravitational radiation, and the observations of that system are perfectly in keeping with the quadrupole formula that Einstein proposed. Beyond that, from 2015 onwards, of course, we've had direct detections of gravitational waves now, very excitingly by interferometers from the LIGO collaboration, what's now called the LIGO-Virgo-Cagra Consortium. and they give direct evidence for the existence of gravitational waves. And not only that, but also information about the systems that emitted them. So these extremely violent mergers of black holes and neutron stars. And finally, we've got cosmology here. So I'm going to put a question mark next to cosmology as well, because over the coming decades, we're going to be getting much more precise information from the next generation of surveys about cosmology, which can be used to test Einstein's theory of relativity. Okay, so let me move on to talk in a bit more detail then about exactly how it is that tests of Einstein's theory are done in the solar system. So in order to test the outcomes of Einstein's theory, it's useful to know what types of gravitational potentials could possibly exist in relativistic theories, and to constrain what those are with different observables. However, we want to do this in such a way that we don't violate the extremely tight constraints on the Lorentz invariance and the equivalence principle, which are given by the huge Revere and microscope experiments that I built on this slide here. So to that end, the class of theories that's usually considered by gravitational physicists when they study experiments and observations in the solar system is what's called the class of metric theories of gravity. So in order to introduce these to you, let me talk about the action for a number of point particles. So I could write down the action for I point particles with masses m in a way that's given by this equation. So here I've got the force velocity of those particles given by u, and g here is a rank 2 tensor that describes the metric of a Riemannian spacetime. Now, if I were to write the action of a number of point particles in this way, I immediately get a number of useful properties. So by determining the Euler-Lagrange equations of this action, one immediately finds that the particles follow geodesics of the metric g. A second property that occurs immediately comes from the Riemannian nature of the geometry that's described by this metric, and that is that there exists local coordinates such that within a neighborhood of a point in space-time, that metric can be described as being close to Minkowski space. So this is the existence of Riemann normal coordinates. And these two properties that follow directly from actions of this type would mean that the weak equivalence principle is exactly satisfied if all particles follow geodesics of the same metric, and that the local Lorentz invariance is also satisfied if there's a set of coordinates we can choose that the geometry of space-time looks like Minkowski space locally. So theories that couple matter to a single metric in this way have these very desirable properties that we want in order to pass the stringent constraints that we get from the huge Revere experiments and the Earth-Verse type experiments. So just as an aside, what another option might look like is if we were to consider matter coupling not just to a single rank 2 tensor, but perhaps to 2 rank 2 tensors in this way. So I've now got m and n as 2 coupling constants between our particles, and rank 2 tensors g mu nu and h mu nu. If one were to consider a hypothetical coupling between matter and gravitational fields in this way, then the conjugate momenta that you'd calculate for the particles, the form momentum p, would have 2 terms, one that was determined by the metric g mu nu and one that was determined by the metric h mu nu. Now, because these are 2 different metrics, we know that in general it's impossible to simultaneously make two different metrics spatially isotropic. That means that form momenta would necessarily be anisotropic if we had couplings to gravitational fields of this type. And the huge Revere experiment constrains exactly that kind of anisotropy. And it would mean that if we did have a second coupling of this type to another gravitational field h mu nu, the coupling constant would have to be 10 to the 27 times smaller than the first coupling constant. For all intents and purposes, it would have to be vanishingly small. So we don't want to consider couplings between multiple gravitational fields and particles. We want a single universal coupling between one metric tensor that describes space-time and all particles that exist within that space-time. Okay. So this kind of action means that gravity is coupled to all particles via a single universal metric. And this this is the essence of what the definition of what a metric theory of gravity is. It's a theory of gravity that couples to matter only through the metric, which guarantees satisfaction of the foundational assumptions that are going into our theory, the weak equivalence principle and local Lorentz invariance. And it's widely thought that only metric theories of gravity, or theories that are extremely close to metric theories of gravity, should be viable. So this is the class of theories that are used as foils against which to test Einstein's theory of general relativity. If you want to consider how we can constrain metric theories of gravity with observations, then it's useful to introduce the parameterized post-Newtonian formalism. So in principle, there's infinitely many different metric theories of gravity that we could construct with any number of different types of fields present within them. We could have gravitational scalar, vector, or tensor fields in any given theory, as well as the metric that couples to matter. So what we want to know is how we proceed to test this infinitely many different types of theories. We clearly can't predict calculate the field equations for infinitely many theories and perform infinitely many tests. That's not feasible. So instead of that, what we choose to do in the solar system is to parameterize the one field that all of these theories are known to share and to which matter responds. And that is the metric tensor. So in the weak field limit in a post-Newtonian expanded metric, we'll take as the background the Minkowski metric. The leading order contribution to the time-time component of that metric tensor is then a term 2 times some Newtonian gravitational field U, which satisfies exactly the Newton-Poisson equation. So if I were to take a metric that had -1 plus 2 times the Newtonian potential in its time-time component, the field equations I would recover would be exactly those of Newton. So Einstein's theory, we know, recovers Newtonian gravitational physics as its leading order approximation because of this. If one were to go then to higher accuracy, next to leading order, there are a number of different possible terms that one could imagine introducing into the theory. So the way that the parameterized post-Newtonian formalism works is to add all the types of gravitational potentials that one could sensibly try and construct. So those are given by the capital letters in each of these terms, the capital Phis, the A here and the V. And then in front of each of those different types of relativistic gravitational potentials, one introduces coupling constants. So I won't go through the precise form of each of these gravitational potentials because that would take, I think, too long for this talk. I'll just give you as an example this relativistic gravitational potential phi1. So phi1 here is the solution to a Poisson equation that's sourced by the mass density rho times the 3 velocity of matter squared. So this is a gravitational potential that's sourced essentially by the kinetic energy density. In the relativistic theories of gravity, this is known to gravitate. Similarly, phi2 is the gravitational field of the Newtonian gravitational potential. Phi3 is the gravitational field of the internal stresses of matter, and phi4 is the gravitational field of the pressure of matter. So the lowercase letters that multiply these gravitational potentials, this beta, for example, the psi, the gamma, or the alphas and zetas and so forth, these gravitational coupling strengths are the contribution that these potentials would make to the gravitational interaction in particular types of theories. So in any given theory, the idea is you could calculate the specific values that these parameters would be predicted for these parameters. And at the same time, we can go out into the universe and observe gravitational phenomena to get constraints on the parameters too. We can therefore constrain different theories of gravity without having to go through each individual theory of gravity one by one, which would be too time consuming. So that's the time-time component of the metric. We similarly can expand the time-space components and the space-space components. And you'll notice that there's some lengthy combinations of these parameters that multiply some of the potentials. And the reason for these particular combinations isn't obvious immediately at first glance, but they're constructed in such a way that the parameters themselves have a particular physical significance when one calculates the physical consequences of putting them in the metric in this way. So let me talk through some of those, the physical meaning of some of these coupling parameters that occur in the PPN test metric there. So the ones that are most frequently tested are the gamma and the beta parameters. So these measure respectively the amount of curvature that's produced by a unit of rest mass and the nonlinearity in the superposition law of gravity. So for general relativity, these parameters take the value 1, and in other theories of gravity, they could take values that are different from 1 in principle. Psi here is a preferred location effect. There are no preferred locations in general relativity, but there can be in other theories. The alpha parameters, alpha 1, 2, and 3, describe preferred frame effects. Again, there are no such preferred frame effects in general relativity, so they take 0 in that case. But in some theories of gravity, it's possible for some of these parameters to be non-zero. And the zeta parameters, finally, are parameters that describe the violation of conservation of total momentum in relativistic physics. So there is no such violation in general relativity. So for all of these parameters, take the value 0 in Einstein's theory. And in lots of sensible theories, these zetas are also 0. But there are some exotic theories in which they can be non-zero. So there's a reference at the bottom here to Cliff Wheel's Living Review, which is a good place to look for more information on this, if you want to find out about that. So with these parameters, we can now go out into the solar system or into other astrophysical systems and see what the gravitational physics that gets produced by them is and what the constraints available from observations are. So if one were to go about doing that, to use observations to try and constrain these parameters, this is the kind of result that you get. So the gamma parameter that shows up in the test metric, and remember that describes the amount of curvature that's generated by a unit of rest mass, is most tightly constrained by the time delay effect, the Shapiro time delay effect from the Cassini probe, which was a satellite that went to Saturn to observe Saturn and its rings. From a relativist point of view, one of the most significant things about that was when the radio signals that came from the Cassini probe went through the gravitational field of the sun on their way back to Earth, there was a very small but measurable time delay effect, and that allowed gamma to be constrained to 1 part in 10 to the 5. One could also use light deflection. So Arthur Eddington's famous experiment, the solar eclipse, constrains gamma. The modern version of that is the very long baseline interferometers, which measure gamma to be 1 part in 10 to the 4. With the beta parameter, remember this tells you about the amount of nonlinearity in the relativistic theory. The best constraints on that come from observations of the perihelion precession of Mercury. So that gives constraints around 1 part in 10 to the 4, as well as the Nordtvedt effect, which is the name given to a hypothetical effect that can potentially arise and which corresponds to a violation of the strong equivalence principle. So this last observation is made by tracking the orbit of the moon around the Earth using retroreflectors that were left on the moon by the Apollo astronauts. So it's possible to bounce a laser off those reflectors from Earth and measure how far away the moon is. And by following the orbit of the moon, we can tell its center of mass is on a time-like geodesic around the Earth at a level of accuracy at about 1 part in 10 to the 4. So this beta and gamma parameters are very well constrained by these relativistic effects in the solar system. And likewise, we have constraints on the other parameters that show up in the PPM test metric, coming from a variety of different places. And again, rather than talk through all of these in detail, I'll refer you to the review by Cliff Wheel that's referenced at the bottom here. So this is how gravitational physics happens in the solar system, how tests of gravity happen in the solar system. This is the leading way that scientists perform these types of observations and experiments. And my goal is to try and extend this same logic into cosmology so that we can try and have a similar kind of framework whereby we can parameterize the types of deviations we might expect from our general relativistic models of the universe, and to use observations to constrain the possible deviations that one might get for metric theories of gravity. So in the last half of the talk then, I want to move on from the solar system to extend these same ideas into cosmology. I want to not just extend them, make sure that those ideas are compatible with the solar system tests as well in the appropriate limit. So cosmology presents us with a new set of challenges that we have to overcome if we want to test gravity in that arena. So first of these is that Minkowski space is no longer a viable background. In fact, we should probably be using a Friedman space, which is a dynamical homogeneous isotropic space, in order to perform our expansions. That complicates everything that we're trying to do because the background itself now has non-trivial dynamics. The coupling parameters, such as that beta and gamma and the alphas and zetas that showed up in the PPM test metric, must now become functions of time. The evolution of the universe in generic theories of gravity would be expected to make those coupling parameters not constants anymore as they are in solar system tests, but functions of the evolution of the universe, so functions of cosmic time. And we must include dark energy, of course. So dark energy is known to exist in the universe. It's required to make the universe accelerate on large scales. Although its effects aren't noticeable in the solar system, they will be noticeable in cosmological observatories. A further technical problem is that we need different approximation schemes in cosmology when we consider different spatial scales. So when we're considering nonlinear structures on smaller scales in the late universe, we need post-Newtonian type expansions, and on very large scales, and in the early universe, we need cosmological perturbation theory. These are technically different approaches, and they're required to use both of them in order to construct a theoretically consistent framework for testing.
Jim, sorry, we couldn't hear what you said in like a couple of seconds. So can you just check your microphone again? We still can't hear you. Yes, we can hear you now.
You can hear what I'm saying now?
Yes, we can. Good.
Okay. Okay, I'll go back to my slides then. So I was saying that testing gravity in cosmology presents a number of challenges, but also a set of opportunities. And the opportunities here include testing the idea of varying constants, as well as providing us with the opportunity to make links between cosmological phenomena and local gravitational physics, which then allows us the idea of complementary constraints on the same underlying gravitational physics parameters. So that is, we can constrain the same gravitational interaction by looking in these different environments to see in which places we can make the tightest constraints and what that implies about the behavior of gravity in other places. Okay, so this is what we need to do in order to test gravity in cosmology. So let me talk you through the approach that I've been using to try and do this. So the first step here is to construct a cosmological model from the bottom up. So what I mean by this is to take small regions of space-time that are described by the parameterized post-Newtonian metric that I showed you before. This is the metric that encodes all of the information about those different gravitational potentials, and then construct from those a cosmology by gluing them together. So this diagram is supposed to illustrate what I mean here. So I've got three different regions of space represented by these dashed lines with perturbations on top of them, represented by this wiggly line. And in order to construct a cosmological model, I need to glue these together in an appropriate way. Because of course, we cannot use Minkowski space to model anything that's larger than around 100 megaparsecs or so. Trying to do that would result in recessional velocities from the Hubble expansion becoming too large to be compatible with the expansions that are being used. So we need to glue these regions together so that locally, each one can be treated as being a post-Newtonian perturbed region of space-time, but globally we end up with something that looks like a cosmology. So in order to do this, we need to apply appropriate junction conditions between these regions of space-time. So if we have curvature tensors in our theory, then the appropriate junction conditions in order to keep the components of those tensors smooth as we go from one region to the next is that the first and second fundamental forms on the boundary between the regions should be the same on either side. That is, the intrinsic and the extrinsic curvature of the boundaries between these regions should be the same on each side. If that's true, then we'll have a smooth geometry, and we'd expect to have a nice self-consistent cosmology. And in fact, the cosmological behavior here emerges from those boundary conditions. So the expansion of the universe can be thought of as the recession of the boundary of each of these regions, and the recession of the boundary comes about because of the gravitational fields of the matter that exists within each of these regions. So if I increase the dimensionality from a one-dimensional line here back to a three-dimensional space, this is the kind of picture that we've got. So you might have two different cubic regions of space-time, and I can glue those together, and I could insist, for example, on a type of symmetry at the boundary, applying those junction conditions and getting a cosmology from the motion of that boundary with respect to the matter inside each of the boxes. So I'm giving you just a heuristic description here, of course, but you can see the mathematics in the reference at the bottom of the slide. The result of all of this is that one ends up with an emergent cosmology with a set of Friedmann equations describing the large-scale expansion that's compatible with the ppm test metric. So what we get are the first and second Friedmann equations that look like this. So h here is Hubble's expansion rate, and a prime is a time derivative. Everything here is defined with respect to conformal sign. And you can see that the first term on the right-hand side of each of these equations looks like the corresponding term in the Friedmann equations of general relativity, except we now have a coupling parameter alpha or gamma in front of each of these mass densities. And the reason for this is because the gravitational field that has the gamma parameter in front of it, the one that corresponds to the curvature of space produced by a unit mass, appears in this first Friedmann equation from the Gaussian Benning equation, in fact. And in the second Friedmann equation, we have an alpha here, which is effectively the value of Newton's constant that you'd measure with a Cavendish type experiment. That appears in the second Friedmann equation because this is an acceleration type equation like Newton's second law for the motion of the boundary. The alpha c and the gamma c on the right here are new parameters that are introduced in order to describe dark energy in this approach, which aren't required in the solar system, but are required in cosmology. So these are the same alpha and gamma parameters that appear in the ppm test metric. And from these two equations, you can derive quite straightforwardly an integrability condition between the two of them, which gives you a relationship that must be satisfied by these parameters. So in this equation at the bottom, the integrability condition, the haps on quantities here correspond to derivatives with respect to the number of e-foldings of expansion. So you get a large-scale expansion here that's emergent and compatible with the ppm behavior of gravitational fields on small scales. And that's because the emergent expansion of the universe here is due to those gravitational fields themselves when smoothed out on the appropriate scales in the appropriate way. So this gives us information about the background, which can be used to constrain the parameters. We also want information about the perturbations around that background in order to calculate the predictions for very many gravitational observables. So below the homogeneity scale, so that's below around 100 megaparsecs or so, we can calculate that the perturbations, the time and the space part of the metric, so phi and psi here, have to satisfy perturbation equations of this sort. So these are derived strictly in the post-Newtonian formalism. You can think of these as being like the quasi-static limit of cosmological perturbation theory. And likewise, we can construct a momentum constraint equation that has to be satisfied as well. So the derivations of these are actually in the papers at the bottom of the slide. And you can see on the left-hand side, we've got combinations of potentials that take the same form as they do in general relativity in the quasi-static limit. And these are obtained by direct transformation using an isometry that exists between perturbed Minkowski space and perturbed Friedmann space on small enough spatial scales. And once again, on the right-hand side, we've got terms that look similar to the ones that appear in general relativistic equations, but containing these parameters alpha and gamma. And because of the way that we've constructed this approach, these equations are automatically valid in the presence of nonlinear structures. So this is how we'd expect the perturbations on small scales to behave. We can also consider what happens on very large scales. So above the horizon size, we can think about the perturbation equations that can be determined using the separate universe approach. So if you haven't come across the separate universe approach, let me explain what that is. So we imagine that we've got an expanding homogeneous universe on the left here. We have the effective Friedmann equations that govern that expansion, so we know exactly how that's going to behave. I can consider another hypothetical universe that's expanding in a slightly different way on the right-hand side of the page here. And this second universe is also expanding in a way that's governed by the same Friedmann equations. So because I know the way that both of these two universes are expanding, I can treat one of them as being a perturbation of the other. And in that sense, I can derive what the perturbation equations must be on superhorizon scales. So this idea, this approach was pioneered by Bertschinger in the paper that I've referenced at the bottom of the slide here. We applied this same approach, generalized it a little bit and applied it to the ppm test metric. And we found that on superhorizon scales, we end up with combinations of gravitational potentials that have to satisfy these equations here. So from that separate universe approach, we get these two different equations. And if we were to boost a set of observers in the second universe, then we also get a large-scale version of the momentum constraint equation. So on the left-hand side, you can once again see that these equations have exactly the same form as general relativity when you're considering linear perturbations around a Friedmann space. And on the right-hand side, we once more get the same set of curvature of space and effective Newton's constant parameters. So the same alphas and gammas, alpha C's and gamma C's describing dark energy on the right-hand side. And once again, the hats on these quantities correspond to derivatives with respect to the number of E-foldings of expansion. So superhorizon perturbations, it turns out, can be parameterized using the same set of parameters that are used in solar system experiments, assuming that they're generalized appropriately to be functions of time and that we supplement them with additional terms that correspond to dark energy. So these equations, unlike the previous set, are only valid for linear perturbations. But because they're derived in the superhorizon scale limit, we only expect linear structures there anyway. So these should be sufficient to describe those very large-scale gravitational effects. Okay, so we can put all of this together then, the small-scale limit and the large-scale limit, and end up with a combined set of perturbation equations that looks like the following. So we have something like a Gauss energy constraint equation in the first one here. The second equation is the Rye-Chowdhury equation, and the third equation is the momentum constraint equation. The left-hand sides here, again, look exactly like general relativity. On the right-hand side, we've got constructive parameters now, mu, psi, and curly g, which we know on small scales from our direct isometry have to take the following limits, and on large scales have to take these limits. So this is just a direct combination of the two different limits that we found before. And you can note here that all of these coupling functions are constructed entirely from ppn parameters and their time derivatives. Okay, so we've got a set of Friedmann equations that describe the background evolution that's compatible with the ppn metric. And we've now got a set of perturbation equations that describe the scalar perturbations around the Friedmann background that are also compatible not only with that small-scale ppm test metric, but also with that large-scale global expansion that we have as well. So let's think about the constraints that we could apply upon these parameters from observations. So this is very much an ongoing piece of work, and I'll just show you some very preliminary results. So if I take the different parameters that occur in these equations, the alpha, which is the effective Newton's constant, gamma, which is the amount of spatial curvature produced by a unit rest mass, the dark energy parameters alpha c and gamma c, and all of their time derivatives. And we get the following set of constraints from cosmological observations combined with observations from the solar system. So you'll note here that the constraint on the gamma parameter is the same constraint that comes from the Cassini probe. And that's because of this synergy that we now have between cosmological gravitational fields and weak gravitational fields in the solar system. It's the same parameter. And it turns out the constraint from the solar system is tighter. So we should use that as our observational constraint in this case. So here the weak field observations are complementary to the cosmological observables. When we're talking about time derivatives, then we need to apply constraints not just from the solar system, but also from cosmology. So alpha prime here, this is the derivative of Newton's constant with respect to the number of E foldings of expansion. The observational constraint on this parameter is it has to be compatible with 0 at 1 part in 100. So this is nowhere near as tight as the constraints on gravitational parameters in the solar system, but hopefully this is the type of constraint that's going to become tighter as the new next generation of cosmological missions comes online. So this alpha prime constraint comes from, in fact, the orbit of the moon, or you get a similar order of magnitude constraint if you consider primordial nuclear synthesis. The gamma prime parameter here was taken from the results of weak lensing from the KIDS survey and 2DF lens. So this is a slightly weaker constraint. It's a constraint that has to be compatible with 0, 1 part in 10. And the dark energy parameter constraints here come from observations of the CMB using the Planck surveyor. And again, these are around 1 part in 100 for the parameters themselves, and around 1 part in 10 for the time derivative of those parameters. So if we work out or display visually what these constraints mean for the different parameters that occur in the cosmological perturbation theory equations that we derived, then we get the following type of picture. We have the constraints on the mu and psi parameters that appear in those equations are very, very constraining when we get to very small scales. And that's because the constraints on ppm parameters are very small on those scales. They come directly from the solar system experiments. When we start going to very, very large scales, so super horizon scales on the left, we have much more freedom, and that's because the constraints that appear on time derivatives of these parameters in particular are much weaker currently. But as time goes on, we would expect to see those constraints improve. We could therefore use the next generation upcoming cosmological observables in order to constrain this type of freedom in gravitational couplings further and further. Okay, and in between here, we've got a simple interpolation. So this is just a TANF function. So I had a recent paper with Dan Thomas and Theo Anton where we investigated different types of interpolations between the very large scale and small scale limits that we have. Okay, so in summary then, and in Outlook, we find that the same gravitational couplings that are constrained by solar system observations very successfully using the parameterized post-Newtonian approach can also be constrained in cosmology. They appear in the background Friedmann equations and in the perturbation equations of gravitational couplings around that background. We know that the gravitational couplings must become scale and time dependent in cosmology. That scale dependence has to be compatible with the superhorizon and subhomogeneity scale limits that we've been discussing. And the time dependence can be constrained using observations directly. And this will allow us to probe the idea of varying gravitational coupling constants in cosmology. So it's something that can be done, I expect, with the next generation of cosmological missions. And it shows us that to make the most of upcoming cosmological observations, we should consider them in concert with other astrophysical constraints. And that's because they're really constraining the same underlying gravitational physics. And we often have a lot of insight about the different types of gravitational interactions that could be possible from the observations that we make in the solar system and elsewhere. So we really should be considering cosmology and solar system and binary pulsar experiments simultaneously to get the best constraints. And I think this shows that the future of tests of gravity also looks bright, that we've got a new arena in which we can test gravity, and we've got new aspects of the gravitational interaction that can be probed in cosmology that simply cannot be probed in the solar system. So with that, I'll finish the talk, and thank you very much for listening.
Okay. Any questions for the audience?
Okay. Is the weak equivalent? Okay, sorry. Weak the is the weak equivalent principle violate in scalar tensor theory of gravity?
So as far as it can be determined observationally, there are no observations that suggest any violations of the weak equivalence principle. So the constraints on the weak equivalence principle come from the microscope mission that I mentioned, and that's a space-based mission that measures the rate of acceleration of plutonium and of platinum and titanium under the gravitational acceleration from the Earth, and there's no violation of the weak equivalence principle to within 1 part of 10 to the 15 at least. So there are extraordinarily tight constraints on any violations that might potentially occur.
So I mean in the so this constant put so okay, I ask this way. So okay, so this means that okay, in the construction of scalar tensor theory of gravity, there are some violation of weak equivalent principle, right?
In which theory of gravity?
Yes, in scalar tensor theory of gravity, there are the some violation of weak equivalent principle or not.
It depends how you construct the theory. If you construct the theory such that there's a universal coupling to matter fields through the metric only, then there is no violation of the weak equivalence principle. But it is possible to consider more exotic cases where one might have more complicated couplings between matter and gravity. In those cases, it is possible that you could introduce violations of the weak equivalence principle. But the most commonly considered scalar tensor theories of gravity are ones that fall into that metric class of gravities. So by construction, they obey exactly the weak equivalence principle.
Okay. So if we to ensure that the weak equivalent principle is satisfied in the experiment, the scalar degree freedom in tensor and in scalar tensor theory of gravity have to be suppressed, right?
No. So it's quite possible to construct scalar tensor theories of gravity that are compatible with those weak equivalence principle constraints. And the Brans-Dicke theory of gravity, for example, is one of the most classic varieties. The weak equivalence principle is valid in the Brans-Dicke theory, and in the Horndeski class of theories, assuming that the metric tensor is the only gravitational field that couples to matter, in that very wide class of theories, there is no violation of the weak equivalence principle.
Okay, thank you.
Okay.
Right. So I think that's all the questions we have, and let's thank for the speaker again. Thank you for the talk. It's pretty good.
Thank you very much, and thank you for the invitation. Okay, bye-bye.